Somebody at home misses this. So let's take a look. Yesterday, I talked a little bit about passive transport. It's how cells get things in and out, right? Cells have a cell membrane. It's kind of like their skin. And just like our skin can let some things in and some things out, the cell membrane of a cell works in a similar way. The word passive simply means that it does not require energy. Today, I'm going to talk to you guys a little bit about active transport. And when you hear that word active, I think about something that requires energy, right? Yesterday, we talked about being passive aggressive, right? So Jerry, let's say Jerry and I, we've got an apartment and Jerry never does his dishes. And I write a note to Jerry, hey, thanks for doing the dishes. That's passive aggressive, right? What would active aggressive be? If Jerry came home from work and I start cussing at him about the dishes, right? Because that takes a little bit more energy on my behalf to be sitting here cussing at Jerry about the dishes rather than passively leaving a note. So passive, no energy. Active, needs energy, okay? And so that's what we're going to talk about today, active transport. Now, where can you find this information? Well, in Unit 4, I have included a PowerPoint. I've also got tons of videos. So if what I'm telling you right now is not making a ton of sense, later on you can watch this 4-minute long video that I made for you guys on YouTube, right? That will go back over everything I'm going to say today. Now, this is an assignment right here that we need to work on getting done sooner rather than later. It was technically due last Friday, but I know the transition to Plan B is, got some of y'all's brains thinking all crazy. And so we'll work on this today. But right now, I want to look at our PowerPoint. Well, we didn't cover all this. We're going to be covering some new stuff today as well. Okay, so let me scroll down to where we left off yesterday. So yesterday we talked about passive transport. Passive transport is how things move in and out of the cell with no energy, and they tend to go from high to low. Just like if you were riding down a hill on a sled, from high up on the hill to low down in the valley, it's passive. That's why it's fun, right? There are 3 types: diffusion, facilitated diffusion, and osmosis. Diffusion will be anything, any small molecules. They can diffuse in and out of the cells. Facilitated diffusion is like when a large molecule needs help. Now, it gets help by these little protein openings in a cell membrane. And the last one is osmosis. How are you going to remember this? I don't know about y'all, but when I look at that word osmosis, I think ooze. I think water oozing in and out of something. But today, we're going to talk about active transport, right? So active transport is the movement of molecules, compounds, or ions across a membrane from low concentration to high concentration. So if you look at this little diagram right here, lots of the molecules are already inside of the cell. There's only 2 on the outside. In nature, these molecules would want to leave the cell. But our cell sometimes needs to hang on to molecules, like sugars, for example, right? You want to eat your food, you want to digest food, and you want to keep that energy inside of you, right? You don't want all that energy and all those nutrients diffusing out of your body. So your body actively has to keep the sugars in the cell using active transport. Usually active transport moves molecules from low to high. Now, what does that mean, or how can you think about this? Well, I think about it again like our sled. We've got low elevation, or low in the valley, and high up on the hill. Now, if I'm down here, low in the valley, and I've got my little wagon, to get my wagon from low in the valley to high up on the hill, what am I going to have to do? I'm going to have to work, right? I'm going to have to use energy. Where our cells use a special molecule known as ATP. You can think of ATP like a battery, right? And this little battery molecule gets charged up by the mitochondria, and then it can be used to provide energy for these different processes. Now, how are you going to recognize when things are active? If it sounds like, if it looks like the cell is working hard to do it, then it's probably active. A lot of times you'll see this word, pump, right? Does the fuel pump in your car require energy? Yes. Does the water pump in your house require energy? Yes. Even if you have one of those old school like pumps in your yard, you still have to use some energy to get it turned on. So anytime you see that word pump, we're talking about active transport. Now let me give you a good example, right, of active transport. The sodium potassium pump. And you're thinking, what the heck? What is sodium? What is potassium? They're both electrolytes. And we talked some about this yesterday. Electrolytes are good for muscle contractions, right? When I flex my muscles, do you think my cells are having to actively pump things in and out for me to do this? Yeah, because if I sit here and flex my muscles, eventually they get what? Tired. And I might be too tired. I might not have enough energy to flex my muscle anymore. So it's not only requiring energy from me, but my muscle cells need energy. What about your brains? Some of you guys can be taking the ACT tomorrow, and I hate it for y'all. I hate tests like that. I'll just be honest. I love teaching, but I hate tests. All right? Now, how do you feel after taking something like the ACT? Exhausted. So what does that tell you about your brain? Do you think your brain needs energy? You know what's really crazy? Your brain is an 8-pound ball of fat. It's mostly fat. So I guess if someone were to call you a fathead, they're not lying. These fat-based cells, these nerves, these neurons, require a lot of energy, right? They, believe it or not, actually generate electricity. Yeah. And that electricity goes from your brain to your spinal cord and then to your muscles and to your heart. Think of it like this. I flatline on the table. My heart stops pumping. What is the doctor going to do? Clear. And they're going to jumpstart my heart. They're literally going to electrocute my heart back to starting. They need to provide energy. Now, don't take a car battery and hook up the jumper cables to my nipples. That's not going to work, right? Because that's way too much energy. You would simply just cook me, right? But that's what they're doing, right? They're providing some electricity. So our muscles and our brain cells, our nerves, they need lots of energy. So they do a lot of active transport, right? And they actually generate electricity. Now let's look at some more examples, right? So like I said, how are you going to recognize these? Well, anytime you see this word right here, pumps, right? These pumps are going to move things from low concentration to high concentration, right? And then we've got some other ones over here, endocytosis and exocytosis. Now, let me give you some cheat codes or easy ways to remember this. Endo in science means in. Cyto in science means cell. So endocytosis is doing what? Actively moving something in to the cell, right? Now, what do you think exo means? Sounds like exit, right? Or out. So exocytosis moves something out of a cell, helps the cell get rid of something, right? So let me put it into everyday conversation. Sometimes our cells will actually engulf or eat things. right? They'll actually change their shape and swallow things in the same way that you open your mouth and swallow a cheeseburger. Uh-oh, sorry. And that would be endocytosis. Your cell is kind of eating things, right? And so another way to think about this is just endocytosis. The cell is eating. Now, what's the opposite of eating? Excrement, excreting, like you could think of exocytosis like the cell taking a poop, right? And you're thinking, what? This doesn't make any sense. Yes, it does. You have immune system cells, white blood cells. They are your body's soldiers. They float around in your bloodstream. And if they bump into bacteria, viruses, or any bad cells, what do you think they do? They kill it. Well, how do you think they do that? They literally change their shape, look like Pac-Man, and then swallow the bacteria and then digest it. That will be endocytosis. Do you think that takes energy for this cell to completely change its shape and then swallow this thing? Heck yeah, man. Right? Does it take you energy to actually eat food and chew food? Yeah. You've got some pretty serious muscles in your face for chewing, right? You can like kind of see them when someone chews. In fact, there are some foods out there like celery that are considered negative calories. Because when you chew celery and you eat celery, you actually burn more calories than you get out of it. So if you were stuck on a deserted island with a refrigerator stocked full of celery, you're in trouble, aren't you? Right? Because no matter how much celery you eat, you're going to starve to death, right? Because it actually takes more energy to chew it. That's why it's a great food if you're trying to lose some weight. Because you're like, I got the munchies, I need to eat something. And instead of eating a family-sized bag of Doritos, you could eat a family-sized bag of celery, and it's almost like you're working out. Because by the time you get to the bottom of that celery bag, you would have burned more calories than you got out of celery. Now, you're going to take a big poop later, because the celery is mostly fiber. But that's not the worst thing in the world either. Now, let's talk about poop, not actual poop. What about a cell performing exocytosis? Let's say a polar bear came strolling in through the door right now. We're all going to be terrified, right? Oh my goodness, right? You guys ever heard of fight or flight? What hormone is your body going to release? Adrenaline. Now, how does this happen? Well, let's look right here. Right outside of your kidneys, right? And your kidneys are right here on your back. There's a gland. It's called the adrenal medulla. And what do you think the adrenal medulla makes? Adrenaline. Now that polar bear walks in and we all look at it and go, oh man, and our brains say, we're in trouble, releases adrenaline. Well, how does that work? Well, the cell already has made a lot of adrenaline, right? Because that polar bear walks in, we don't want to wait for our body to make adrenaline. We want to already have it stored and stockpiled, right? So that when that moment comes, our brain can release it faster than you can blink, right? Because if you've ever been scared, and you've ever been in a car accident before, like a fender bender, right? Everything happens so fast, and then all of a sudden you realize it's all over with, and you're like, wow, man, like, your brains can react to things really fast. But anyways, adrenaline is released this way. The cell's not just taking a poop, but the cell has made this hormone, adrenaline, and it waits to the right moment. And then it opens. And then that adrenaline floods into your bloodstream. Some of you guys are fighters, and I wouldn't want to scare you, right? Because what would your reaction be? I jump around the corner, boo, and then maybe Tay hits me with the right hook, knocks me out, right? He didn't mean to, right? That was just his response, right? Maybe Parker walks in, and I say, boo, and he takes off running down the hallway before he even realizes why he's running. And there's actually a third one. You're so scared, your pants, right? That's something that adrenaline can cause. Now, unfortunately, you think, oh, I don't want that. I want to be the fighter. I want to be the flighter. But if it really were a polar bear, the person who puts up their fight, are they really going to beat the polar bear? No, one swipe at the I don't know if you guys know how tall polar bears are. Like even on all fours, it wouldn't be able to come into the door. And if it stood up on its back legs, it wouldn't fit in my room. Right? Its paws would be probably pretty similar to the width of my desk. So if you try to fight it, obviously one swipe with the paw and you're going to be flying across the room like a rag doll, right? What about those of you that think you can outrun it? Not even Usain Bolt, right? But those of you in here that your response is to defecate or urinate your pants will be the most likely to survive. Because your ancestors survived with playing dead. Because most time when animals die, what's the first thing that happens? Their body's just kind of released, right? And any excrement they had in their body gets released, right? And so that's just a survival strategy. We'll talk more about that when we get to natural selection. But again, the release of hormones, that's an active process. Your cell has to try to do that, right? Here's another one. You ever heard like drunk with love? Right? Someone's so in love you can't think straight. You ever seen puppies and kittens like on, TikTok or YouTube? They're like in a box, and they'll fall out, and you feel like the, oh my gosh, right? You see a baby and you just feel this weird sensation. That's actually your brain getting stoned off a hormone known as oxytocin. You also get that same hormone when you give someone a hug or you kiss them on the lips. And your brain has to actively release that hormone, oxytocin. It's actually called the hormone of love, right? And it's actually very, very vital hormone. People that release more oxytocin are generally healthier, happy people, right? And so that whole saying like hugs, not drugs. Well, if you're hugging someone, your brain is actually releasing a drug that will actually make you feel mildly high. It's called oxytocin. Right? And we'll talk about the evolutionary reason why our brains have these compounds that we have to actively release, right? We'll talk about that later, though. Okay, now, in just a minute, I'm going to give everyone a piece of paper, and I'm going to have all of you guys write what I write down. It's going to be a cheat sheet that I want you to put with your laptop, so tomorrow when you sit down to take my quiz, you will have that cheat sheet right there next to you. Who made the quiz? Who's telling you what to put on the cheat sheet? So what do you think is going to be on the quiz? What I have you put on the cheat sheet. If you're at home, get out a piece of paper right now. I have paper for y'all. You just need a pencil or pen. If you don't want to use paper, if you want to like type it or draw it on your computer, you can do that as well. But I think there's something special, especially now more than ever, doing something on with paper and pencil. You're welcome. Did everyone get one? Okay. All right, so papers and pencils ready. Where'd it go? All right. So it's kind of like monkey see, monkey do. What I write, you write. What I draw, you draw. And tomorrow your quiz will be nice and easy. All right. So first thing, okay, I want you to write is the word passive. Okay. And then next to it, write no energy. Okay. I'm going to go ahead. I'll leave it open all day. I can even release it today if you'd like. Okay. Oh, yeah, I forgot about the ACT. How many other juniors we got? How much time we have left? We'll do this. I'll open it right now so that if you get it, you know, you can start it right now while you're here in the room. So if you have trouble with the question, what are you going to do? You're going to ask me. And so you're going to get it done while we're here. And so tomorrow, what are you going to do? The ACT. And then you can do anything for biology? Unless you have missing work. All right, so let's get on this, guys. Thank you for bringing that up, Jerry. Passive, no energy, okay? So on this side, I'll use a different color. We're going to write active. And so what am I going to write here? Needs energy. Okay? Over here under passive, I want you to do this. I want you to write high to low. So passive transport goes from high concentration to low concentration. So what do you think active does? Low to high. And you might be thinking, well, Mr. Collins, what the heck? Like, I need to visualize that. Okay, let's do it, right? So we'll draw a tiny little cell, and I'll fill it with tons of little molecules. Just put a bunch of tiny little dots inside of your little cell. Now, where's all the stuff? It's highly concentrated in the cell. So where does the stuff want to go? It wants to spread out, right? So we'll draw an arrow out. Now, what about this example? We got a cell, but this time, draw as many dots as you can inside of your cell. I'm actually going to erase some of my dots that I made on the outside. Okay, where is all the stuff? It's inside the cell, but sometimes our cells are really greedy. You might have already a ton of sugar in there, but your cell's like, I want more. And so we're going to go from low to high. So this cell's going to pump that stuff inside because it's going to be going against the gradient, right? So here are some other words that you might see. Uh-oh. You might see moves with the concentration gradient. Don't be scared of that word gradient. When you drive up 181, Highway 181 or down 181, like you're going up to Linville, it's really steep, right? There's actually signs on it with trucks, and it says caution, steep grade ahead. So when we talk about gradients, that's talking about steepness, right? And so passive likes to go downhill, right, with the grade. So what are we going to write for active? Are we going to go with the flow, or are we going to go against the flow? We're going to go against the flow, right? We're going to go against the gradient. So with active, you'll see moves. Uh-oh. Change my color. Moves against. Moves against the concentration gradient. They're going against the flow. All right. Now, what are some examples of each? Because you'll see questions that'll say, osmosis is an example of passive or active transport. So let's do the examples, right? So we've got 3 types of passive transport. We have diffusion, we have facilitated diffusion, and the last one, osmosis. Okay? And then I'll give you a little hint for each of those in just a second. Now, what are some examples of active transport? Anytime you see the word pump, and I'm going to put that in quotations, okay? The most famous one is the sodium potassium pump. He's telling a story. You guys know Sheehan. In our muscles, we actually have a calcium pump. Yesterday, we talked about electrolytes. We talked about muscle cramps. When you have a muscle cramp, it's because those calcium pumps aren't working properly. There's not enough electrolytes for them to work. The other one, or other ones, is endocytosis. Remember, endo means into or inside the cell. Endocytosis and exocytosis. Okay? Now I'm going to give you a little hint to write down for each of these. Okay? So for diffusion, it's the movement of small molecules. So for example, is oxygen a big molecule? No, it's tiny, right? So if I give an example, EX for example, oxygen is tiny. It's only 2 atoms. So when I breathe air in, do you think I have to work to get that oxygen to dissolve into my blood? No, it's tiny. Where is most of the oxygen? In my lungs. Where does it want to go? It wants to spread out. So what it does is it diffuses into my blood. And that's why if I were passed out unconscious, CPR works, right? You give the compressions to circulate the blood. You could literally blow air into my mouth and the oxygen will passively diffuse into my blood. Now, sometimes the molecules are kind of big. They want to go into the cell. They want to diffuse, but they need help. So facilitated diffusion, protein, usually like a channel or something like that. A protein helps large molecules move. A famous example, in our cells, we have a little protein, it's an opening that lets glucose, which is a big molecule, right, into our cells. And that's facilitated diffusion. Why does glucose need help? Because glucose is big, right? Glucose is C6H12O6. So glucose has 24 atoms. So it's a big molecule, right? It needs some help to get in our cells. Okay, last one. Osmosis is the movement of water, right? You guys have seen in the movies, somebody like passes out of dehydration or something like that, and they're in the desert, and they take a rag full of water and they squeeze the drops of water into the person's mouth. The person's passed out. Can they drink the water? But if they put the water in the mouth Where is the water going to go passively? Right into your skin, right into your lip, right into your tongue, straight into your bloodstream, right? Especially if you're dehydrated, right? Because there'll be more water in that pure cup of water than is currently in your body. So osmosis is movement of water. Okay, now let me give you some hints for these other ones right here. For the pump, again, the famous one is the sodium potassium pump. Now, these also involve proteins, right? So sometimes they're just simply called protein pumps. So if you see the question talking about protein pump, if you see that word pump, that's active transport. Endocytosis is, let's do into the cell. And again, think Pac-Man, right? Let's say this is our cell. Right? And maybe this is a bacteria, right? So endocytosis, that cell is eating, right? It's almost like the cell's eating. The cell's got to open its mouth and swallow it whole, like our white blood cells. And so exocytosis exits the cell, right? And so maybe, right, let's do, so maybe at first the cell looks like this, and inside of it is a little vesicle. It's like a little chamber full of cell waste, right? And then as time goes on, time 2, the cell starts to release the waste. Right? And so the cell got rid of the waste. Just getting it out. Yes. Yeah, absolutely. Okay. Okay, do we have all that down? I'll give you one more second to get all that down. And then there's 3 more words we need to write down, and then I'll let you guys start your quiz. Then you'll finish it, and that way tomorrow, if you're a junior, you don't really need to worry about biology other than makeup work. And if you're not junior, just focus on your makeup work. Does everyone have this? Does anyone need more time? Raise your hand. Are we all good? Okay, last thing. Hypertonic, isotonic. You can write on the back wherever you want. Hypotonic. Okay? Really salty. So hypertonic, really salty. Isotonic, I want you to write equal. This will make sense in a second. And then hypotonic, less salty. Right? Because hyper means like above, right? Means really high. Hypo means below. And iso means equal. Okay? Now, this is talking about an environment, right? And so if I have a cell that is in a hypertonic environment, it means this environment is really salty. And what do we know about salt and sugar? What does it do? It dries you out. It sucks water out, right? And so in a hypertonic solution, water is going to be sucked out and the cell shrinks. In isotonic, everything is equal. So is anything going to happen? Nope. Right? The water, some of it will leave, but the same amount will go in. It almost looks like an equal sign, right? And so no change. The cell is not going to be affected. The cell is very happy, right? And then last one, and then you guys can start your quiz. Hypotonic, I think hypo-hippo, that always helps me remember. Hypotonic, that's supposed to be a Y. Sorry, it's really hard to write with a mouse. Hypotonic. And I'll give you the perfect example of hypotonic is distilled water or pure water. It's always going to be hypotonic. And what was the example of hypertonic we talked about yesterday? What's a really salty, sugary drink? Soda or Bojangles sweet tea, right? Soda has got a lot of sugar and salt. So soda makes our cells shrink. It actually dehydrates us. But if you drink pure water, you're going to hydrate, right? And so what does that mean? In hypotonic solutions, water enters the cell, right? If you drink a glass of pure water, most of that water is going to go straight in your bloodstream, right? Now, what does that mean? What is the cell going to do? It's going to swell up. Okay, everyone got that? Okay. Now, what I'm going to do right now is I'm going to go ahead and stop sharing my screen. I'm going to go ahead